Okay, we're recording.
Well, I will start more formally. I welcome those here today and those who may be watching the recording of what we hope and expect will be a really stimulating and important conversation today about marine cloud brightening. And we have with us someone who probably knows as much about and is involved with and has the details more than probably anybody on the planet, Professor Stephen Salter from Edinburgh University. I looked up your bio and I was going to read some of it, but I think what I will do, yes, what I will do is, in less than 1 minute, I will turn it over to you. I only want to make two comments. One is, as we've discussed and as you've seen, Stephen, from previous meetings, I know that science is important, but in addition to giving us enough science and engineering, what we want to know is, how close are we to doing this? What are the barriers? How can we help you? And so forth. And in terms of your bio, the one thing I did notice when I took a look is apparently last year you were elected to the Scottish Academy of Engineering or something like that. So you are a member in good standing of the Hall of Fame. I think it was the Scottish Hall of Fame of Engineering. So welcome, Stephen, and thank you.
Right. This is actually the number I got from a lady called Julia Slinger, who used to run our Hadley Centre. But the problem is we are retaining 1.7 watts per square metre, too much. Okay, and this slide shows you the amount of sunlight that's coming in against months of the year here, June and December, and degrees of latitude. So that's the North Pole here. And it's a bit of a surprise to see that there's more energy going into the South Pole in December than into the equator. And the reason for that is that it's coming in over 24 hours. So that takes up the difference in the angle. So if we want a number for the average of what's coming in, about 340 looks as if it's pretty credible, but you might do better if you could migrate between here and here. Right, so we've got 340 watts per square meter coming in and 1.7 watts per square meter too much. And that tells you that the problem is only 0.5%, which really doesn't sound too bad, 0.5%. That's another reason, by the way, for picking on the 340, because it's exactly 200 times the 1.7. Right, now, the trouble is that we're getting lots of rather bad things. This is anomalies showing that there's a lot more warming going on in the top end, 5 degrees centigrade there, and we thought that was absolutely terrible. And a way of showing this is a wonderful diagram by a chap called Lee Robinson. And we've got years starting 1979 going around clockwise here. Those are all the years. We've got the radius here is the volume in the Arctic ice as predicted by a mixture of computers and observations. And the months of the year are the green ones here coming down to the black one here. And the radius of this is the volume of ice. And you can see that it's spiraling inwards to getting very, very close to not having any for September. However, all that dims into tiny concern when you look at what happened just a few days ago, where we've got an anomaly in the Antarctic. I think they said it was 40 degrees. That doesn't show much on this diagram, but if we go from 0, which is this white one, we're going up to the reds and through a brown and into more reds here. So we're going up right up to this area here. And that would be predicting about 30 degrees above what it ought to be in that part of the Antarctic. A bit colder down here, maybe that's a good thing. Right, let's see what's happening on the ground. This is somewhere up in Greenland. And as the top ice melts, it leaves behind all this soot and rubbish and mess from previous years. So while the white was very good reflecting solar energy coming in, the black is brilliant at absorbing it. And also, if you look here, you can see all these melt ponds, which are very good at absorbing the heat. And you can see what a difficult place it's going to be to work here. This is very slippery. If you fall into here, you'll live for about a minute and a half. Not very good. And another diagram here. This is the all the IPCC predictions of what this Arctic ice ought to be doing. The mean of all of them is this black line here, and this is the range of all the estimates. And the red line is what actually happened. So this is not a very good advertisement for the IPCC. Every time they bring out a report, it shows how wrong the previous reports were. Now, the policy of the UK and lots of other governments is to cut emissions to zero by sometime. There's a very bit of variation of that. And I plotted this against the years of the various international conferences. We just had Glasgow here. And a statistician looking at this might deduce that having these conferences is actually making it worse. There's a very strong correlation in the wrong direction between conferences and rising of CO2. I'm sure that isn't actually what's happening, but there's probably quite a lot when you have thousands of people traveling around the world to come to the conference. Okay, now this is showing a tiny little dot here. You may think that's just a mistake, but there's a tiny little dot there, and that is supposed to represent all the energy that is used by humans, all forms of energy, nuclear, oil, everything, the whole lot. And the information for that has come from a very interesting review from BP. The link to it is up here, and I strongly recommend anyone who's interested in energy to take a look at that. It's everything you could ever want to know about all the energy. And it comes out as a way to compare this with the solar input. So all this orange stuff here is what the 340 watts per square meter is doing. So that really tells you in your gut the difference between the solar input and what we've been doing. Okay, now this chap here his name is Sean Toomey, and he was very interested in, have I flipped something? No, I haven't. He's very interested in why some clouds looked grey and some clouds looked white. And he was able to get an airplane, and he could fly over the clouds, and he could measure the solar energy coming down from above, and he could measure what was coming up from below. So he could work out what the reflectivity of the clouds was. And he was able to also fly into the cloud and scoop up the drops in the cloud and measure how many there were per cubic centimeter and how big the drops were. So he's a very useful, valuable experiment. And he was interested that some clouds looked white, and some looked a bit grey, and he worked out all the differences in the calculations. And you can boil them down to some algebra like this. Climate people talk about albedo, which is almost the same meaning as reflectivity. And the albedo depends on the depth of the cloud, the liquid water content, then the number of cloud drops in a cubic centimeter here. And that gives you that algebra. Now, if you want to do the engineering, you actually want to know what you're going to do this by controlling the number of drops in the cloud, and you want to rearrange that equation to see how many cloud drops you need to get this amount of albedo for this cloud depth and this liquid water content. And unless you're a brilliant mathematician, this doesn't mean nearly as much as plotting graphs. And here are some graphs of the Toomey equations. What I'm doing here is I'm varying the most important axis here is the number of cloud drops per cubic centimeter. And here I'm varying the thickness of the clouds from 100 meters up to 1,000 meters. And this is fixing the liquid water content to this number here, which is a middling sort of number. And here we're seeing the reflectivity. So this is reflectivity for various cloud thicknesses against the cloud drop concentration. And very similar graph here, except here I'm fixing the cloud depth as 300 meters, and I'm varying the liquid water content from 0.1 to 1. So the middling is right here. And you can see that these are strikingly similar shapes and slopes. And you can show that in this way here, where what I've done is I've taken a particular starting point, let's say this point on this red curve here, and that's corresponding to 10 drops per cubic centimeter. And what I've done is I've doubled it and then gone back to the same cloud depth. And I've doubled it again and then gone back to the same red curve, and then doubled it again, back to the same red curve, doubled again, the same red curve. And you can see that these steps are really very, very similar, maybe a little bit small here, but it's looking as if what matters most is the number of cloud drops in a cubic centimeter, and also that doubling them increases the reflectivity of the cloud by about 5%, about 0.05. Okay. And this is the typical conditions are somewhere in the middle of this diagram. So it's a useful number if you want to do a quick calculation about the change, that doubling the number gives you 5% more reflection. And a lovely way of showing this is due to Schwartz and Slingo. There have got 4 different vertical axes there which are showing the same things, either power or albedo or at the top of the atmosphere or top of clouds. And what you do is you pick any number here that you want. We should say we want to increase the reflectivity by 0.05. Okay, we start along the red line, we run along the red line until we hit the black line, and then we drop down. And this is telling you that doubling the number is giving this 0.05. If you wanted to get a bigger reflection, we go up to here, we run along here to there, and this will tell you that you want 4 times the previous value. If you'd have to, here you're doubling it, here you're multiplying by 4. And it's amazing that you can put such a lot of very valuable information onto one slide. I think that's great. This is showing a lovely pocket demonstration of the Toomey effect. There's 2 jars of glass balls, and these are 4 millimeters. And it's the same material, the same clear glass, and these are 40 micron. And you can see that this has got a reflectivity of about 0.6, and this is a maybe 0.9. And if you count the number of doublings that you'd need to count that, it fits quite well, even over quite a big range like that. Well, this chap, which we call John Latham, was interested in the climate problem, and he knew all about Toomey, and he wondered if we could cool the Earth by increasing the concentration of cloud drops by spraying filtered seawater, tiny, tiny submicron drops of filtered seawater. They would evaporate, and the salt crystals would be lovely for increasing the number of drops in the cloud. To make a cloud drop, you need to have a humidity that's slightly above 100%, and you need to have some kind of seed called a condensation nucleus to get it started. Okay, and over the land, there's maybe 1,000, 5,000 per cubic centimeter of dust and mess and general rubbish, which we're breathing in and out. But over the sea, the air is much cleaner because it's been washed out and falling down and the rain and so on. So over the sea, there's a shortage of these condensation nuclei, and he thought we could maybe increase them by spraying this filtered seawater. And he did some calculations about how much you'd need to spray, and if you do it more or less anywhere, he thought we'd need about 30 cubic meters of water a second to undo all the damage since pre-industrial times. If you're a bit clever and choose the best places, there's a lot of variation. You could get it down to maybe 10 cubic meters of water a second if you pick the low-hanging fruit. And if you put all these numbers in here, we've got the power we want to reflect. And well, I did this at about 1.6 watts, maybe a little bit higher now. So here's power we want to reflect. This is how much we'd need to spray to get this much power, depending on where we did it, depending on whether we're doing it in the clean air in the Pacific, or not quite so clean in the Atlantic. And there's tremendous range in what the initial numbers are. And that's assuming these numbers here, which are reasonable, I think, I don't know. But if you want to express a different opinion, I can change that. And the number that you're starting off with is really very important. And these are maps from a chap called Bellina, where he's showing the cloud condensation nuclei for December, January, February, March, April, May, June, July, August, and so on. And you can see there's a big area where we're talking about maybe 20 per cubic centimeter. The boundary between the dark blue and the cyan is maybe around about 30. Okay, so that's promising. And he did another lot of work showing what's happening through the months of the year for different places. That's the subtropical Atlantic, and here's the Southern Ocean, and so on. And by the way, the green little bits are what's happening now from phytoplankton, and the blue is what's happening from other stuff. So phytoplankton are making a big contribution, and we're doing the same job as the dimethyl sulfide that they're putting out. Okay, well now, back in 2002, I was working on a project to try and increase precipitation of rain. And I measured the relative humidity over the sea, and typically it's about 60% if it's a sunny day. But if you come very, very close down to the sea surface, it shoots right up. And it looks as though there's a very thin layer of very high humidity just at the sea surface. And this is stopping the evaporation. Water molecules are coming out of the sea at the speed of rifle bullets, and they hit an air molecule, and this bounces a lot of them back in again. So it's as if the sea is covered with a sheet of plastic that's stopping the evaporation. And I said, why can't we punch through that layer and get the water able to evaporate? And the idea was to get a new kind, well, a rather old design of wind turbines called a Darius, the ones that look like egg beaters, vertical axis spinning like this. And what I want to do is to have the blades hollow. I want to have them sticking below the sea surface so the water could get into the blade, and then it would be centrifuged out along the blade. Once you've got the blade full of water, you don't have to have it below the surface. And then we wanted to squirt this spray out through the trailing edge of the egg beater wind turbine. So this would recover a lot of the kinetic energy with the jet. And I did the calculations, and with quite a small turbine, you'd be getting 1 or 2, maybe 3 cubic meters of water a second squirted out as small drops. And what we want to do is to have them evaporating with enormously big surface area and having the salt residues fall down into the sea before this humidified air reached land. And if you do some of this, you could sort out the California drought problem by having a string of these along the coast. And John Latham heard about this idea, and he rang me up and said, could I make the spray for his project? And I said, yeah, I can do that, no problem. That wasn't actually totally accurate, but I started working on it in about 2004, and we got to the point now where nearly all the engineering that I can do has been done. And what you really need to understand is the size of the drops. And this all goes back to some work by a chap called Kohler, I think it's 1936. And he's showing what happens if you put drops that were of different sizes into the atmosphere. If you put one that's very small, let's say 100 nanometer drop, once it's out of your machine that made the spray, the size of the drop depends just on the local relative humidity. If it's getting higher, water will condense on it, and if it's the low humidity down, it'll go down, and you'll get a smaller drop. So this is moving up and down here according to what the relative humidity is. If you get this up above this number here, 100.2 7.3 or something, it then gets over this hump, and then it can keep on growing without limit by taking more water vapor out of the air. And I want to spray, because of this, I want to spray water that starts off at the 3.5% solution and an 800 nanometer drop, and that has 10 to the minus 14 grams of sodium chloride in it. And Kohler says that we really don't need a very big extra hump here at that point to get over and then to grow without limit. If you're doing it smaller, then you may not be able to get over the hump. But another feature is that if there is a mixture of sizes, the big ones nucleate first. Then they grab the water vapor because they have a lower threshold for getting over the hump. When they do that, they're scooping up the water vapor, and so these poor chaps here get left out in the dry, and they have a smaller chance. So I'm very keen on trying to get the drops that John Nathan wants, all exactly the same size. Imagine a group of infantry who've been trained to do all the bayonet movements exactly the same. Now, they don't stab each other, but they would if they were different sizes. So let's show you where that is.
Stephen,
Yeah?
I'm sorry. Could you? I'm kind of lost you back there, and I'm wondering if maybe other people are as well. What exactly is the hump? That's if you could just go over that one more time. I'm sorry.
You have to read about Kohler, and what he's doing is he's finding out what humidity you need for a nucleation to grow a cloud drop. Okay, and he's showing that if you are too small, you have to get to a very high relative humidity to produce a proper larger cloud drop. The cloud drops are up to 28 microns, and you were starting with something that's below a micron perhaps. So there's a cube. If you cube the ratio of sizes, you see the enormous amount of water vapor has got to be collected to grow a full-size cloud drop. And this is showing that small drops aren't going to work very well. Does that make sense?
Thank you. Yeah, that clarifies.
Interestingly, this is 10 to the minus 14 grams, and the weight of a COVID virus is 10 times smaller than that. So it would be quite interesting to know what happens if a 10 to the minus 14 grams of salt hits a virus. We're very good at killing bacteria. Okay, for that, don't hesitate to interrupt again if you ask a question. Right, now, you would have thought that, if engineers were running things, you'd have thought there'd be a fairly even distribution of sizes of aerosols in the atmosphere, but there isn't. There's three separate modes, and they're called the Aitken mode, the accumulation mode, and the coarse mode. And here we're plotting the slopes of the sizes of the histograms. And there's not very many coarse modes, so really this is showing a very low curve here. What I want to do is to spray at this size here, the red size, that's 0.8 of a micron. And if this was to evaporate completely down to a dry salt crystal, it would be, which is what the aerosol is really all about, that would dry down to a sphere of 200 nanometers there, or it's more likely to evaporate down to a cube of about 130 nanometers. So that's what I want to do. And it's significant, I think, that there's a gap here between this accumulation mode and the next one along. And I don't understand why there's the gap there. It's maybe because this is very, very good for nucleation. Anyway, I thought that was a nice indicator of the size. And then I found out about work by a chap called Greenfield, and he was interested in the nuclear fallout and how long it took nuclear material after a atom bomb dropped to be removed from the biosphere. And this is a log curve here. This is called the aerosol collection efficiency. This is how fast it's going to be going. Look, it's a log time, so there's 10 to the 4 difference between there and there. And he's got this, what is called the Greenfield gap. And the size of the spray that I want to release and the partly evaporated one here, or the complete dry crust, are all fairly neatly in the Greenfield gap. but there was a paper by some people in Norway which showed that if you had spray in the Aitken mode, it actually worked in the wrong direction. And also in the coarse mode, it worked in the wrong direction, which is again pointing to the fact that we really want to have a rather narrow spread of drops. Whether this is the ideal one, I need a cloud physicist to tell me, and I've asked them and they don't know. But it also, this is a nice size for, if you look at the filter technology and the technology of making the spray, this is a sort of equal balance of miseries in all directions. So that's the one that I want to go for. This is showing the results of a package called COMSOL Multiphysics, showing the effects of different drop sizes. Here we're showing what size of nozzle you need to squirt through. Here we're showing the pressure that you need to squirt it with. And this is the frequency of the drops coming out of a single nozzle. And this is the total power that you need for one of our spray vessels, which is surprisingly flat here. And the one that we picked on is this 800 nanometers. And this says that we need a pressure of 80 bar to squirt water through this size of nozzle to make a nice drop. That's what the engineering is all about. Now, some interesting calculations you can do. We want to know how much solar energy we're going to reflect, how much energy that we'll be getting rid of, and how much energy we need to make the drop. So the energy they reflect depends on the projected area of the drop, which is pi d squared upon 4. A number for the amount of energy coming into the top of the cloud. I've done to 170. I'm assuming half of it's got lost getting down to the clouds. How much we reflect, reflection coefficient, and how long they last. I think drops will last a bit longer than that, but let's put that rather conservative number in. And that's saying that a typical cloud drop will be reflecting 370 microjoules of energy. Okay, and now we need to think about how much energy we need to make a drop, and it depends on the surface tension of seawater, is that number there. Depends on the surface area of the sphere, and this is telling us that it's 150 picojoules. Now, these guys up here are microjoules, and these are picojoules. And so what we want to do is to do a ratio of these two. The energy that's reflected is this much more than the energy we needed to make a drop. 2.3 times 10 to the 9. This is a fantastic energy ratio for what we need to make a drop to what that cloud is going to reflect. And maybe I was being a bit mean saying that's only one day. So it's that makes this technology exciting. Very, very small area of spray is reflecting a tremendous amount of energy because of this ratio here. Our efficiency is not very good at the moment. I mean, if we can make it better, but that's what's the starting point of this calculation. A billion times more being reflected than we needed to make. I can't think of anything else as good as that.
Stephen,
right.
Stephen, yep. We're 25 minutes after the hour, and I just want to make sure that we'll have time for you to, sort of show us how this is applied and have some conversation.
I will accelerate. Okay.
Okay.
This is how much spray is being sprayed out at the moment. The average is of all these red dots is here, and if you look at a very thin black line here, that's what we would have if we had 1,000 of our spray vessels working full power all the time. So what we're doing is we are rearranging the size of the drops. We're not really contributing any more salt. That's there. Now, this is how we're going to make them. This is a wonderful picture from Lord Rayleigh, Medicine, taking photographs in 1878. And this is how we might be doing it. We want to get a silicon wafer, etch tiny holes in the silicon wafer and squirt the seawater through them. We actually want to make them very small holes on one side, joining a much bigger hole on the other side. We need energy to do this, and this is the final technology of sailing vessels. Imagine tying reef knots in the middle of the night in the middle of a hurricane. Unbelievable. This is a sailing ship with sails, but with an extra addition of propulsion, which is the spinning rotor. And this is called a Flettner rotor. A chap called Anton Flettner built this. He sailed against an identical conventional hull from the Baltic to Edinburgh. And here he's coming under the Forth Bridge. That's his real thing. Sailed to America. Everyone was very excited. And then the Depression came along and nobody needed them all. But they're starting again here. And this is how we're going to get the power to move the ships through the water, dragging propellers. This is the Flettner rotors, and we got propellers down here. If you work out the sums, these put a tremendous drag on the vessel. And so I want to instead go to hydrofoil vessels, and I want to have them changing pitch and using the changing of pitch to make them flat. I'm going to skip that horrible thing. This is me, variable pitch hydrofoils on either side here, changing the pitch. So this one is going up and down, driving a pump mechanism here, pumping high pressure oil to make the energy that we need to make the spray. It's amazingly similar to an earth moving machine. And this is using some technology that we developed for wave energy, where you're controlling a big hydraulic machine with a computer. And we started this for waves, and this is the size of the company a few years ago that's doing this. And they converted a JCB earth mover, and the digital hydraulics technology that we developed to do clever tricks is halving the fuel consumption of that JCB. This is a later design where you can see the hydrofoils driving some pumps in here. This is the very latest one, and all the hard work is done in these little compartments here. And one of these is reserved for anybody who wants us to try and make iron salt aerosol. We can give you some power and we can give you some workspace. What we can't do is to carry enormous weights of material, but we can carry some and give you a few tons of payload. That's showing the inside of the works. I think if you're not engineering, you won't be very interested. I just want to show you this to show you that it exists. This is how it might be packaged inside the hull. And I've got drawings for all the contents of all these things, which I could send out to contractors to make it. They're all quick change release, so that we won't be trying to do any clever work there. We'll just be pulling out canister, putting in the replacement, and then be able to work again. Now, this is some very interesting work done by people in Norway, showing the effect of increasing the number of condensation nuclei just by 50%. This is the mean of a large number of spray vessels, and you can see that we're getting very valuable cooling up to 4 degrees Kelvin up in the Arctic there, which is good. And also we are increasing the precipitation in all the dry bits. There's 20% increase in this bit of the Sahara, and quite a lot in Australia and South Africa and Mexico. So that's what happens if you increase the number of condensation nuclei just by 50%. This is showing how the intensity of a hurricane varies with sea surface temperature. 11,000 dots here, a whole lot of different hurricanes. And what we can do is have ships that are tracking the growth of a hurricane. Hurricanes start over on the African side, the ones that Americans get worried about. We could have them cruising around in this area and checking the sea surface temperature and adjusting the number of spray vessels to get the sea surface temperature pattern, what the governments of these countries say they'd like to have. No one's brave enough to promise no more hurricanes, but we couldn't say we'll get you down from 23.4 to 21.4 perhaps, if you'll pay us. So they'd be cruising around here. To begin with, they'd have to do quite a lot, but because of this, some of this cool water can come around again, it gets easier when you do it. These photographs were taken in the same week, showing what's happening in Australia and Kenya. And we can affect that by having flotillas cruising east or west in the Indian Ocean. This is information from the Australian research lab. So this is how rainfall in Africa and Australia are affected by temperature. There's another complication for El Nino events over on the other side. If you've got different missions, killing off an El Nino would take us 2 years for, get rid of that. I need a couple of hundred vessels to do that. To get rid of Arctic ice, I think I only need 40 vessels to do it in 60 days. That's just based on the rate of ice loss and the latent heat of ice. It's assuming that we're not, there's no change in the water and the wind. We can do barrier reef. I think the most exciting one is it's getting sea level down. Over 20 years, we need about 400 vessels to do that. Okay, now, why is that not going down? Am I not showing my, can you hear me still?
Yep.
You can hear me.
Yes.
Yeah. Stephen,
Right.
just on the Arctic ice loss, is that the current loss? So you would be offsetting current melting, or
I'm assuming that the current and the wind are the same. Okay.
no, but the warmth that you're offsetting is existing melting, I assume. It's offsetting the current warming.
But the ice is melting at a rate of 25,000 cubic meters a second. And if I know the latent heat of ice, I can see how many joules is that. And then I can see how much cloud I'd need to reflect in order to cancel that out.
Thank
you. For some reason, my PowerPoint is not responding anymore.
We're seeing it flip through slides here.
Okay, it's doing it now. I was working on the clicker. Right. Here we are. We're giving you the number of spray vessels working flat out. We probably wouldn't have them all working flat out, so maybe you want to have 800 of them. Right. This is an interesting experiment of where I got a rather small spray source, 10 kilograms a second. One of our vessels will do about 3 times that. These are different wind speeds and rise times and boundary layer depths and so on. And I was putting the Toomey equation into a diagram with different spreads of wakes. This is a narrow angle and that's rather a wide one. I didn't know what the spread would be. And I put the equation into that. And I applied this to a real cloud image to see how much the brightness of the cloud is changing. And it's not really very convincing. And the reason for that is shown here. I've got 20 bars with means that there's a 5% brightness difference between each of these bars, which is how much we need to double the reflectivity. And if you look at this and count how many bars you need to have to see there's a gradient, most people think it's 3 or 4. Okay, and that means that your contrast detection threshold is 15%, and we only need 5% to solve the whole problem. So the reason we couldn't see that is because it was just too below our contrast threshold. If I took 100 slides and added them together, you can see these wakes here coming up nicely. Okay, so what's it all going to cost? Well, it's a commercial secret what a thing is going to cost. If you told anybody what it really costs, you lose your job. So what you have to do at this stage is to look around for something that's made in similar sorts of numbers with a similar sort of power and complexity and weight and so on. And the only thing I can find that made in similar numbers is these corvettes. We needed a lot of them in 1940, and they cost £60,000 each then. And they were 2 megawatts, and they were 900 tons. We are 300 kilowatts, and we're about 90 tons. And so I'm just indexing this. Instantly, it's about 100 PhD graduate salaries for building one of those in 1940. So if we look at that, that's costing about £3 million for one of those today, which is about $4 million. and I'd want to have a fleet of 800 vessels, and that would cost about 2.4 billion to buy this fleet. That's probably, I hope that's more than we need, but let's say we did do that. And if you want to spend 2.4 billion, you need to borrow the money from the bank. You need to have about 240 million a year to own a fleet like that. And the reason that I picked 800 vessels was that 240 million pounds is less than the cost of the policing for security for COP26. So having I expect there's a bit more on all the airfares, but the Scottish police said that's what it's going to cost to look after all the delegates to COP26. And we could have solved the climate problem for less than the police for the one conference. This chap is not very enthusiastic about, he was a professor at Chicago University, and he came out with this and he got very wide publicity and was given a chair at Oxford as a result of that. And I will now stop there and maybe I can try and answer a few questions.
Well, thank you so much, Stephen. You saved the best for last. Isn't that pretty extraordinary? The cost of security for COP26, you could operate a fleet of 800 of these.
Yeah, that's right.
So I will just open it up for questions. I'm sort of speechless. So if you could, maybe if you could take that off the screen, Stephen, stop sharing. That way we could see everybody, and just raise your little.
I hit stop share.
Okay, yeah, we're back together.
We're good.
Okay, Stephen, could I open up a comment? Thanks. That was just great, and like getting all of the mathematics. I don't understand the detail, but seeing it there, it just shows how the drop size issue is a key to the efficiency. Now, what I wanted to raise was the impact of a fleet of spray vessels in the Southern Ocean, because the way I look at it, brightening the band of clouds across the roaring 40s and 50s would create a sort of barrier between Antarctica, which is our world air conditioner, and the rest of the planet. It would slow the melting of the sea ice in Antarctica. It would slow the melting and calving of glaciers. It would slow the melting of icebergs in the ocean, and it would slow the increase of the ocean currents that are flowing from the Southern Ocean up into the Pacific and Indian and Atlantic Oceans. Now, we've just in Australia had what we call an atmospheric river, whereby the high temperature of the ocean has caused the dumping of more rain than we've ever had before, with 16-metre floods destroying towns. And so if we were able to cool the temperature of the currents flowing out of Antarctica into the Pacific Ocean, then the driver of that atmospheric river would be mitigated. Yeah. And so I think it's an excellent proposal, Stephen, and the thing is that Australia's already made a start with the Harrison work on marine cloud brightening for the Great Barrier Reef. And so what we need to do is get the Australian government to, I think, start off talking with New Zealand and then the small island states and some of the leading world powers on field testing of marine cloud brightening for the Southern Ocean. And so I feel that the geopolitics of a start in the Southern Ocean is possibly best around the world, and I hope that we'll be able to move forward with that with the Australian government.
Well, I did apply to them. There was a call for grant applications. I did apply and they turned me down. Daniel Harrison is working testing ISOs at the moment, but he is using a spray technology which I fear is got a much wider spread of sizes. And quite a lot of what he's spraying is in the Aitken mode, and it might work the wrong way. And if he can get measurements of what he's actually warming or cooling, he might get rather disappointing results because of this widespread. He knows about this. I've been in touch with him. He visited Edinburgh, and I've said that he ought to look at much narrower spread sizes, and I hope he will take that on board. I could send him the engineering drawings for a way to make the spray. I would much prefer to have tested it, but it would be available. It's using the technology that I could make something myself in my workshop, and there might be ways of making a much nicer one with additive technology rather than machining. But I don't know enough about that to be sure. So I agree it would be a very good place to start. To begin with, I actually want to do it on a single thing on land, on a lonely island with soggy beaches, where I've got clean air coming in from a long way upwind and be able to measure clouds downwind. But there's a few islands that look very good for this: the Faroes, and maybe the Aleutians, and maybe the Falklands. I'd like to learn all the climate physics from something on land, and independently of that, I want to build a hydrofoil vessel that's just able to carry 3 people and be towed on the roads. And I want to learn all about the mistakes with hydrofoils without having to do any spraying. And then, having got all the miserable bits done, I'd then bring them together. There's lots of work that could be done with climate models. The best work at the moment is being done in Norway, and they've got some very good people there. But what I want to do is to get an everywhere to everywhere transfer function of what marine cloud does. It can have effects a long way away in the other hemisphere even, and some of them may be bad, and I want to know about those before we get too deep into this. We could do that by running a climate model where we're randomly switching on or switching off different spray sources in different places. And if you know the random sequence, you can pick out the thing that caused the result with a large number of competing signals all jumbled up together. This technique is used in electronics, in telecommunications, and we call it pseudo-random coded modulation. And we've had one very successful PhD that tried this out as just one little chapter of a PhD, but we can't get any of the climate models to replicate it, which is a very big puzzle to me. I just thought there'd be a feeding frenzy of them all piling in, wanting to say that how they've used it and how they really thought of it themselves at the beginning, but no, they don't want to do it.
So do you agree the Southern Ocean would be a big starting point?
A very good place. But there's nothing to stop you having in the Southern Ocean for 2 months. I can get from the Southern Ocean to the Northern Ocean in about 3 weeks. These spray vessels move very fast when they're we're not using the energy. So you can have whichever ocean you happen to want to be in for moderating hurricanes or stopping sea level. Wherever you do it, it'll stop sea level rising. So that's a very, probably in the medium term, that's our worst worry. In the short term, the Arctic is really serious because we're so close to losing all of the ice. But in longer term, the sea level rise is going to affect a whole lot of rich pink people who've got coastal properties. There's an orange person, I wouldn't mind losing his property, but it's very, very serious in the short term for people in the Pacific Islands. But not long after that, a lot of important cities are built on the coast. And a bit of sea level rise will concentrate the minds.
Yes. Let me turn it over to Ron.
Thank you, Stephen, very much. That was, just kind of overwhelming. But although I've heard you many times in other forums, I have two questions. Quick ones, hopefully. I think you've kind of answered the first one that Robert asked. My understanding is it's important if you're, for the cooling to be, at least according, based on the models, somewhat symmetrical. So if you cool a lot in the south, you want to kind of also do that in the north. So that's sort of a global issue. Is I wonder if you could comment on the recent well, it's a preliminary paper on the effect of cutting the sulfur that's emitted by ocean-going cargo ships in the Atlantic and Pacific, and the effect that may be having on increasing warming. If there's a way to somehow use marine cloud brightening as an alternative to sulfur, perhaps on those cargo ships, or
well, we don't have to be on the ship.
Sorry?
We can certainly compensate for the fact that we.
I'm sorry, we're getting a lot of echo here.
And people need to get specifically on themselves if they're not talking.
But please mute yourself.
Ron, you can mute Manager.
So once that comes back.
Right.
Okay. Sorry,
Steve,
can you repeat what you were saying?
You can certainly correct for the warming that's coming inevitably from cleaning all the bunker fuel from ships. I don't particularly want to put it on the ship. It doesn't have to be anywhere near the ship to do the job, because it's the effect spread out nicely. The ship owners want to get from A to B as quickly as possible, and that might not be the same places as would give us the best results. I want to have this as a wind-driven thing, because if I did it on a conventional ship, I'd spend a great deal of time going to and coming back to refuel or feed the crew or whatever. So this is why I want to have unmanned sailing vessels. They can stay at sea for maybe years, and they're probably better at sea than they are growing weed in a harbour. So I want them there all the time, maybe not used all the time, but directed by clever people running clever climate models to say where the best result's going to be. And, bad trouble in Kenya, okay, move 3 flotillas across to Indonesia, that kind of decision. And with the improvements in weather forecasting, which are very, very good at the moment, if you can predict the wind direction for the next few days, you can tell exactly what's going to go where and tailor the result. And now you can run climate models fast enough to actually predict what will happen in the next few days.
Can I just ask you a follow-up? Do you think that this preliminary result, that it's up to 50%, global warming, just from reducing the sulfur content from about 4 or 5% to I think 0.5%, it seems like a massive kind of example of the potential of aerosol cooling over the oceans.
This is what got Sean Toomey working. When we had the first satellite images come on, they found these strange long streaks and they traced it to the aerosol dirt in the dirty fuel. That's what got the whole of the Toomey work going. To see a ship track needs to have at least 40% contrast change. If you look at how bright they are, they're really striking sometimes. And I'd rather have that effect much thinner and much more widely spread from a lot more different sources. But that shows it's going to work.
Okay.
All the ships also go along the same paths. They're all in the Great Circle routes.
Okay, let me turn it over to Daniel. You've had your hand up.
Okay, thanks. Yes, Stephen, I just wondered, there was a question actually within an email thread, and it came Ye Tao, I don't know if I pronounced his name right, from the Mir project.
No.
And he said something which it really, I thought was a sort of shocking statement, really, which was that this would need decades of research. I remember in the email.
Well, I've been working for nearly 2 decades. He's probably quite right, yeah. But we've had the 2 decades. John Latham did this in 1979.
Good. Well, I think he was implying it in these decades of further research, but I mean, I'm happy if it's if we can count the decades that have already happened, because I'm thinking, you know, we don't have decades to play with before implementing something like this.
Well, it's only one person who didn't know much about cloud physics at all to start with. But I think we could have the first full-size vessels go ready for sea in about 5 years. And if you put enough money into it, you could maybe do it a little bit quicker than that. But if you're just doing it at a sensible rate, 5 years, we could have the first vessel. I'd like to have a single one without the ship, just working out of an ISO container, and maybe in 3 years, on land with power from a wind turbine or something clean. He's very keen on, I think, doing it with mirrors on the ground, and that would certainly work. The worry I have is that if you want to get rid of 0.5% of the energy coming in, you need to cover 0.5% of the with a perfect mirror of the land, of the surface area of the Earth, and that's a lot. If you work out how much per person, it's a great, you know, lots of area. And the trouble is, you've got to keep it all clean. That's okay, but you might decide that you want to move it around. We might really want to have them in the southern hemisphere and then move to the northern hemisphere. So it's not easy to suddenly switch them off or move them. And I'm claiming an advantage for marine cloud brightening is we've got seasonal and regional control, and you can turn the whole lot off with one mouse click, and it's all forgiven and forgotten in the next time it rains, which is just a few days. So we've got tremendous control and tactical use. You can say we're looking, a nasty cyclone is building up in the off so-and-so. How quickly can you get a couple of flotillas along there? You really want to run the hurricane control starting the previous November, doing it in a very gentle way and watching the sea surface temperatures and deciding that you're overdoing it or you need a bit more. And that could be quite a lucrative way of funding it.
Great, thank you.
So it's the agility and the mobility that's a huge advantage.
Yeah.
So the safety and risk factors for marine cloud brightening, I think following on from Daniel's question, can be compared to the safety and risk for other interventions such as stratospheric aerosol injection and ocean ion fertilization. And I think that one of the beauties of your work, Stephen, on marine cloud brightening is that it appears it's very simple and safe. It's just adding salt to the air, and so it's like an initial technology that can be deployed while the further research goes on the governance and safety and risk and side effects of some of these more complicated technologies. And I think the comparison to stratospheric aerosol is really quite key, because the governance issues there just seem far more difficult than the governance issues for marine cloud brightening.
They've got to get it right first time as well, because they'll be stuck with it for months or maybe sometimes say a year or two. I hope they will get it right, but I think it's very nice to be nippy and agile and able to respond quickly.
Stephen, if I could, if I were to, or would I be able to approach my Congress member, for example, and ask him to circulate a document or a proposal to the U.S. Department of Energy or whatever in the alphabet soup of U.S. agencies there are? Would you have a document or a set of documents?
I'll send you a whole bundle of documents, and you can pick the one you think would be most effective. There's ones that I'm trying to put everything on half a page, and ones that have got 40 or 50 pages long. I think it's very difficult to get through these days. I've tried to all the people in the UK government. There's a government department, and they have now. They said if I send it to individuals, they would blacklist me, and my emails wouldn't get through. And they seem to have done that now. I had to send it to an inquiries desk, and I have done that now, and I now don't get any acknowledgement back, except I used to get one saying they wanted to do it within 15 days, but I don't get even that now. It's just staggering that they just want to avoid the blame, and they just say, oh, well, the IPCC say so-and-so, and we're believing them.
I'm wondering whether you have tried, or some of us could try to approach some of the high-profile climate journalists in the United States. I'm thinking about people like Dave Roberts and Robertson Meyer, is it, from The Atlantic, and others who are pretty sophisticated to do a story. Has there been, as opposed to the sort of the popular press, has there been a story done by a serious climate reporter, either in the UK or anywhere else?
Not serious. There've been a few things, but they've been really rather superficial.
I mean, I would think that would be a valuable thing to do. Would you agree with me or others?
I would be delighted if you would do that, yeah.
I mean, I'm wondering, again, my focus here is how can we take this to the next step and not just move on and you're out there trying to knock on doors literally or figuratively, and people aren't answering the doors.
Yeah. I'm starting a little company which is to be called Ocean Cooling Technology, and I'm trying to raise the money that I need to take this further. I think we can answer all the real difficult questions for about 10 million, and we could be having all the hardware technology done for probably less than 100 million. And I'm hoping that I can use crowdfunding for this. I did have a very miserable time crowdfunding on a project for clearing anti-personnel mines, which worked very well until people forgot about Diana, and it faded away. And the end time of that, when you're running out of money and you've got people, family to feed, it's a very, very miserable thing. So I was suspicious about crowdfunding. I can put in my life savings, which I could put in £1 million for it at the moment, and I'm willing to do that. But I'd rather do this knowing that if it worked, this would then trigger the next chunk of money.
That's I mean, that really says so much, that you're willing to put your a good chunk of your life savings and all the rest of it. And I certainly, from what I've heard, and I suspect others share my thoughts, that it's certainly a worthwhile endeavor. I'm wondering, I just sort of throw this out now, would there be a couple, maybe 2, 3, 4 of you who would be willing to continue on with a smaller conversation with Stephen that focuses on how to take this to the next step and brainstorm with you and so forth? Does that make any sense either to you, Stephen, or is there anyone willing to do that here?
Yeah.
I see Mark has raised his hand. Robert, Leslie, maybe the 3. I don't want to make it too large a group, but I mean, I don't want to make it exclusive either, but maybe 3 or 4 of you. So we have at least Mark and Robert and maybe Daniel and Leslie for a start. And just to continue in a smaller way, we'll bring back the ideas to the larger group if there were anything we focus on. But I don't want to just leave this today, and say, okay, here we are, and in 2 weeks we talk about something else. I want us to be able to.
I would be delighted.
Okay.
And there's also the potential to share the recording of this talk, which I think should get a scientific audience, a broader scientific audience, who can see that there's quite a coherent argument that Stephen is presenting, which does offer a very big challenge to the current climate orthodoxy.
Yes.
So
I'd like to get a team of about 5 young engineers, graduates sort of mid to late 20s, to argue with me and point out all my mistakes. And at the moment, I'm having to pretend to be a group of 5 people by dropping something and leaving it alone for 5 months and then coming back and pretending I'm a critic trying to spot things. It's now getting harder to spot the mistakes, but there will be still some, and I want to be, it's much better to have a small team who are doing constructive criticism of each other. And that's what I'd like to do. And I can maybe just about afford to get that going.
I wonder if Leslie, some of your students or your colleague students can play that kind of role with Stephen.
You know, I'm wondering if, and as I said, my class is actually filling up, but if you would want to lecture to, who knows who's going to show up this year. I had 30 enrollees last I checked, without even publishing who's speaking when yet.
I would be delighted to do that, yeah.
Aha, okay, good, yeah.
All right.
Could I just suggest we invite David and Mike to comment before we close off the meeting?
Absolutely. Let me introduce or have Mike, I think most people know Mike. Take 30 seconds, introduce yourself, Mike, and then make your comment or ask your question.
Can you persuade somebody to try coded modulation?
Well, let me just say that I think there is a U.S. project on this effort, and that's the one that's going on up at University of Washington, right? That
Rob Wood.
And that Kelly Wanser and others in Silver Lining are doing. So there is a U.S. project on this thing. So I'm not sure going to the U.S. government's going to get anywhere. I mean, there's that effort going on.
I think the U.S. government would want to have the money spent in America. Kelly Wanser came across to Edinburgh way back, and I showed them all the ideas that I had for making spray. And they said, could they bring a spray expert along? I said, I'd love to talk to a spray expert. And they brought a chap called Armand Neukermans, who is a pioneer inkjet type. And he's done a lot of work on spray generation, but I think his method is making too wide a spread of drop sizes. And he is convinced that my ideas will not work because of the clogging of the nozzles. I really respect his ability, and he knows a lot about nozzles and about spray. But the big difference between the technology you need for an inkjet printer and the technology that you need for pre-filtration for a reverse osmosis. And the filters that I want to use are on the market now for cleaning up the water that's going to go to a reverse osmosis membrane. And the factory that makes them says I've explained what we want to do. They do it by having a black flush ring. They have a ring of filters, and one of them's got the water going the wrong way through it, and then they change it to the next one. So all the clogging that's building up, which they may have to do every few minutes, is flushed out by taking the turn for some of the flow from all the other ones. Now, you don't do that with inkjet printers. You've got to get it really, really good. And I think there's such a big difference that back flushing makes it possible to have all the plankton removed down to about 20 nanometers before it gets to the nozzles. There's also 200 million nozzles in each silicon wafer, so I can lose a few million nozzles without it really being a problem. But Mike, I would love it if you could get someone interested in the coded modulation. I have tried and failed.
Mike, do you have any other follow-up?
No, just that we probably ought to try and get some of this other group to speak to the group.
Well, yeah. I'm in touch with Rob Wood. In fact, he gave me that photograph of the South America. He gave me 100 images of clouds, which I was used for detecting the spray. They're using a much smaller size than I think is right, and they know a lot more about cloud physics than I do, and would be useful to find out what it was. But I think their spray is in in the Aitken mode and might be working in the wrong direction.
Well,
They're just interested in the cloud physics. I don't think they're really hands-on drilling holes, nuts and bolts engineers. And that's me, rather having to painfully learn some cloud physics.
Yeah, well, the importance of bringing these together. We have tried, Mike. We on our list last fall was one of the key people to bring on to speak the same way we had Rafe speak was Kelly Wanzer. But when I contacted an aide, I was told she didn't have the time at the time. I don't know if any of you have a better contact with her. We can talk about that offline, because from everything I know about her and their work, it would be a critical, wonderful connection to make. So with that, I'll wrap it up. What can I say except this is an amazing opportunity. Thanks so much for your perseverance all these decades, Stephen. It's got to be incredibly both exciting and lonely at times. And I certainly want you to know that whatever we can do to support you, we will. The 3 or 4 of us who volunteered will be in touch with you, and we'll just start brainstorming. We'll see if we can get anywhere. Stephen, you want to have a last word or two?
Yes. If anybody sends me their email address, I will send them lots and lots of different papers. I can deluge you with bundles of papers. I'm about at the point where I could send the drawings and the calculations out to subcontractors. I want to sort out all the IP business. Doing that could stop some investor putting money in that we might need. So I'm a little hesitant to do that at this stage, but we could very soon get people to say what they would sell them for to us.
Well, that's great. Again, well, thanks everybody for participating, attending, and we'll see you all in 2 weeks. And have a good morning, evening, afternoon, middle of the night to the rest of you, wherever you are. Thanks again. Bye.
Thanks.